for the morning session Wednesday. So until now, we have seen mainly three themes. So we have discussed how to do sequential hypothesis testing, and we saw how you can do that adaptively, and in cases where non-adaptive techniques also work well. We had, in that theme, we had the talks by Annie, by Chan, and by Kira. And then yesterday we discussed about inference through the talks by Vivek and Panos and Ilan, and also the talks by Hannah and Anis in the previous day. And also Steve talked also about inference, but also included strategic component, the strategic component and incentives. We're going to see more about incentives tomorrow. Yesterday afternoon, we talked about the situations where the input is mostly IID, but you're going to be robust to cases where you have some adversarial components, some worst case components. So we had the talks by Hara, by Julian, and by Victor in that line of work. So what we're going to do in this session is that we're going to move towards the worst case extreme, and we're going to try to think about worst case approaches. Now, a typical drawback of worst case approaches is that they tend to be very pessimistic. So in the theme of the information workshop that we're having, we're going to discuss what information can you have about the future in order to be able to achieve enhanced performance in your system, so not revert to the worst case. So this is generally the theme of learning augmenting algorithms, and this will be the area, the subject of this first session. So we are going to try to understand what information can we add to classical worst case approaches in order to improve the performance when this information is accurate, gracefully degrade with the performance when it's not, and still retain the worst case guarantees, while also we're going to also discuss learnability and how we can learn. So our first speaker will be Yossi Azar, who's joining us virtually. Yossi is a professor at Tel-Aviv University. He has done phenomenal work on online algorithms, scheduling, and multiple other aspects on the online decision-making branch of theoretical computer science. And without further ado, Yossi, take it away.
Okay, thank you. So first of all, I would like to thank the organizers for inviting me. I was supposed to be there in person, but unfortunately, I had to cancel the trip last week, but I'll still give the talk by Zoom. So I'm going to talk about a very basic and simple problem of flow time, also called the response time, with uncertain processing time of job on a single machine. And this is a joint work with Stefano Leonardi from Rome, and Noam Touitou, which was my graduate students from Tel Aviv, and he graduated a couple of months ago and started a move to Amazon. And actually, also the slides were prepared by my student Noam. So the problem is, I start immediately without any directly with the problem. I'm talking about jobs which are released over time on a single machine, and each job queue takes processing time, certain processing time called the PQ. And in the online scheduling problem, the jobs are revealed upon the release time. So only when the job is released, you get to know its processing time, and you really know that these jobs exist. And the algorithm has to do only some very simple task to decide which job to process at any point of time. And now we move to the goal function. The goal function is to minimize the total flow time, also called total response time, which is precisely the sum over all jobs of the difference between the completion time and the release time of the job. It's actually the amount of time that the job has been in the system. And you just sum it up over all job. And this is actually the total flow time, which is equivalent to average flow time, average response time. All these things are the same. And let me just take a simple example. Let's say that this is the time line. At time 0, you have two jobs, the blue one whose processing time is 2, and the red one whose processing time is 5. And let's say that I decide to process the red job until time 4. At time 4, a green job is released whose processing time is 2, and I decide to switch to the green job. So I haven't mentioned yet, but you are allowed to do preemptions. Preemptions stop a job start a different job, and then return back to a previous job. So let's say that we process the green job for 2 units of time and we completed it, and then we return to the red job and complete it, and then to the blue job. So if we now compute the response time or the flow time of each job, so the green job is great. It has a minimum possible response time, but the red one is 7 and the blue one is 9. And then we just sum it up and get 18. So this is a very simple and basic problem. And it's what's nice about it that it actually has an optimal online algorithm. So this is and the algorithm is just to process called SRPT. At any point of time, we process the job with the shortest remaining processing time. This is an example of a very rare situation in online algorithm that you actually get one competitive algorithm, which is actually equal to the optimum solution, although you're in an online scenario. And the algorithm is very simple. Just process the shortest remaining, the job with the shortest remaining processing time. The thing is that you need to know the exact processing time of the job upon its release. And this is hardly happens in the sense that you typically know the size, approximately the size of the job. You're not sure about the exact processing time. So instead of, so this is like one extreme where you know the exact processing time. So if you are not sure about the processing time, you can look at the completely other extreme, which is called non-clairvoyant setting. In this case, the job sizes are not known in advance. Actually, once you finish the job, you know its processing time. So this is like the completely other extreme where you don't have any information about processing time. And then here the situation is it's not as nice. And instead of one competitive, you have actually competitive ratio, which depends on the size of the input. It's not a fixed competitive, it's not even 2 or 10. It depends on the size of the input. And then, of course, there is a difference between deterministic and randomized algorithms, but it's not constant in any way. But this is completely the other extreme. So now the typical case that we can think of is that you have an estimate of the processing time of the job. You know approximately how much it will run, but not precisely. Then we look at the following scenario. When you get a new job, again, jobs are released over time, and only when job is released, you get to know that it exists. So you get an estimate, PQ tilde instead of PQ. The PQ is a real processing time, but you get an estimate. How you would get such an estimate? First of all, you can get it from the user. The user knows what type of job is sent to the system, so we can give its estimate. Alternatively, you can do it by heuristics. You can analyze sometimes the algorithm. You can see how many loops and what's their structure, and get an estimate on the processing time. And even more, in a more sophisticated way, you can use a machine learning prediction where you consider many attributes of the program and decide and provide a prediction on the processing time. And the idea that, okay, so now we don't know precisely the processing time, so we cannot be one competitive, which means we cannot achieve the optimal solution, but we want to get an online algorithm whose competitive ratio depends on the accuracy of the estimates. By the way, I don't have on the slides the definition of competitive ratio. I assume that everyone knows it, but let me just mention it for completeness. Competitive ratio of the algorithm is the ratio between the performance of the online algorithm compared to the optimum offline algorithm that knows the whole sequence, the whole input or the whole sequence of input in advance. So you compare the performance of the algorithm, the online algorithm, with the optimal solution that have all the information in advance. So we want it to depend on the accuracy of the estimates of the prediction of the processing time. Of course, if the estimates are excellent, you want it to be small, but if the estimates are really far away from the truth, then there is no way. I mean, you assume that the competitive ratio it's not going to be so nice or so good. So now the question is how to measure the accuracy of the estimates that you are provided with. So there are two types of errors. Either your estimates are larger or smaller from the real size of the job. So you might have an underestimation factor, which means that the job is really longer than what you estimated. And the maximum ratio is called mu1. So these jobs are really larger than what you estimated. And there is an overestimation factor, which is, of course, the maximum ratio of the estimation divided by the real size of the job. So overestimation, the real size is smaller than the estimation, and you look at the maximum ratio. Note that these two types of errors or estimations are really different in the sense that during the algorithm, you can, for example, you can process a job and then figure out that its processing time is longer than what you expected, and then realize that you are in the underestimation regime, while overestimation is a bit harder because you are given many jobs and some of them could be very short, but there is no way to find which jobs are really shorter unless you process all of them in some sense. So these two types of errors are not completely symmetric, but still we view them in a symmetric fashion. And we define the distortion as the product of these two factors, mu1 and mu2. Please note that somehow if all estimations are actually twice, let's say twice the real size of the job, then the mu1 is actually 2. Mu2, you can think about it as 1, but actually you can think about it as also half. And then the way that we view it is the distortion is only 1 because it's 2 times half. So in some sense, we want to claim that if our estimations are, let's say, precisely twice the size of the real job, we really want to get an algorithm which is very excellent in the sense that is very close to 1 competitive, because the distortion is very small, is only 1 in that case. So it's a nice property of this definition. But typically both mu1 and mu2 are going to be larger than 1. Okay, so now the next question is, do we know the distortion in advance, or we only realize it while we process the jobs during the algorithm? So, so in general, we want to get, as I mentioned, an algorithm whose competitive ratio is a function only of the distortion. And the interesting thing is we can, like, one natural algorithm to use is shortest remaining estimated processing time instead of shortest remaining processing time, because we have the estimation instead of the real size of the job. Unfortunately, this algorithm is not only not one competitive, it's actually in some sense infinite competitive. It depends on the ratio between the size of the jobs, and it's really a very, surprisingly, a very bad algorithm. And I'll give you a intuition why this happens. If you process a job and actually you finish it, so the estimation, the shortest remaining estimation processing time is 0, so this job would get highest priority, although it might be still long time is left, and you would process this job instead of processing short jobs, and that causes very high competitive ratio. And so it turns out that, like, the natural algorithm is not competitive at all when you have a distortion. So as I mentioned, I want to look at two cases. One is that the distortion is known in advance, and the other that it is not known. So if it is known in advance, I call it robust algorithm. This is a non-standard name. Okay, robust is used for different algorithms, but not specifically in this area. And here, for every parameter mu, which is the known distortion, I want to get an algorithm, alg mu, which depends on the known distortion, and its competitive ratio is f of mu. So here I have a family of algorithms, or an algorithm with a parameter, and the competitive ratio depends on the distortion. A much stronger notion, it's what's called distortion oblivious algorithm. Here we assume that we don't know the distortion in advance, and here we have a single algorithm called alg, that for every distortion mu, the algorithm is f of mu competitive on input with distortion mu. So please note that I'm looking at, as was mentioned at the beginning, on the worst case input. I want that my algorithm will work and achieve the performance for every possible input and for every possible error in that sense. So obviously the second notion is what we prefer, and it's a much better algorithm. Obviously, distortion oblivious implies mu robust, but not vice versa. So this is what we want to achieve. And our result from SODA 22 is as follows. We present a distortion oblivious algorithm, deterministic algorithm, which is mu log mu competitive for every possible input and for every possible distortion. And this is the first distortion oblivious algorithm for this problem. And we also show nearly matching lower bound, which is omega of mu. So you cannot hope to get something which is sublinear depending on mu. And for every, even for randomized algorithm. So let me just explain what it is. So let's say that you are you have an estimate which are 1 plus epsilon compared to the real size, or twice compared to the real size. In that case, you get a constant competitive algorithm. So obviously you wouldn't get one competitive algorithm, but you will get constant competitive algorithm, small constant, while running shortest remaining estimated processing time might get you infinite competitive algorithm. So this is the result. And now I'm going to switch to a more general problem, which is called weighted flow time, which is actually exactly the same as flow time, but each job has some importance, which is called weight. And now the goal function, instead of being just the time in the system, completion time minus release time, which is the time in which the job is in the system, I multiply it by the importance. So there are more important jobs, and they are weighted with a larger weight. And the goal is actually to minimize the weighted flow time or weighted response time. Okay, so let's take again an example that we already used before. So here we have, again, two jobs. One, the processing time is written inside the rectangle, and the weight is written above the rectangle. So the blue job has processing time 2 and a weight 2. The red job is longer, it's 5, but it has higher importance, 6. And let's say, so I decide to run the red job until time 4, and then I get a green job, which is very short, but also has high importance. So jobs which are short and have high importance would have higher priority in some sense, because like shortest remaining processing time prefers shorter jobs. And here, if they have a higher priority, it would even prefer them more. So I'm going to switch to the green job and finish it, and then switch to the red job and then finish the blue job. So again, if we look, it's the same as in the previous example. The green job has a processing time, or a flow time or response time 2, and the red one has 7, and the blue one has 9. But now we multiply by its importance. So the 7 is multiplied by 6, and the 2 is multiplied by 8, and the 9 is multiplied by 2. And then we get 76. So this is just the weighted response time or weighted flow time. Now, surprisingly, this problem is much more complicated than the unweighted version. And now, even on a single machine, even when we know that precisely the processing time of each job upon arrival, again, we are in the online problem, still we cannot get constant competitive algorithm. Specifically, the competitive ratio would depend on the P, either P or W, where P is the ratio between the largest job to the smallest one, and W is the ratio between the maximum weight to the minimum weight. Again, weight is important, it's the importance. And already in STOC 2001, Chikuri, Khanna, and Zhu proved the log square P competitive algorithm. Then Nikhil Bansal and Damder proved in SODA 2003 log W competitive algorithm. And actually, a few years ago, we with Noam, from a student, we improved the log square P to log P. So here again, this is assuming that we know the exact size of the job upon its release time. It's still an online problem, but we know the processing time upon release time. Here, we generalize it to the case that there is a distortion, that there is an error, that we have only estimation. So here, if mu is the distortion, we get mu square log W. Again, W is the weight, the ratio between the maximum weight to the minimum weight, or mu cube times log mu P, where P is the ratio between the largest job to the minimum job. But unfortunately, now we don't have a distortion oblivious algorithm. We just have a mu robust, which means that we need to know the processing time, the distortion in advance. We need to know an upper bound on the distortion, and the competitive ratio would depend on this upper bound. Spoiler for the end, this is an open problem, how to get a distortion oblivious algorithm for the weighted flow time on a single machine. We don't know how to achieve it. Again, we cannot hope to get much better bound, at least for constant distortion. Like a natural scenario as the distortion is small, 1 plus epsilon, 1.5 or 2. And then in our algorithm matches the previous competitive ratio for the case that we know the size, the processing time of each job precisely upon its release time. Okay, so let me summarize the results that we have. So we have two cases. One is mu robust, where we know the error in advance, or an upper bound of the error in advance, versus distortion oblivious, where we don't know the error in advance. If we, for distortion oblivious, which is a much nicer notion, we only know how to deal with the unweighted case, and we provide an algorithm which is mu log mu competitive. While for the weighted case, we need to know the distortion in advance, and we get also worse bound because it's a weighted case. It's more complicated case. We get a mu square competitive algorithm. Now, a natural question would be: can we remove somehow in a black box fashion the assumption that we know mu in advance? Actually, this is like, can we, like in a black box fashion, get a mu robust algorithm and create a distortion oblivious algorithm? So, like a natural way to do it would be the following. Let's guess the distortion. So let's guess the distortion and pretend that we know the distortion. This is something which is typically used in online algorithm, which is called doubling. You guess, and if your guess is incorrect, you fix it. The problem is that we have two types of possible errors, obviously. Either our guess, we have overshoot in our guess, or undershoot. Let's say that our guess was much larger. Okay, the distortion was 2, but we guessed 1,000. So the competitive ratio would depend on 1,000 and not on 2. So we actually get omega of our guess and not of the real distortion. So let's be more, so this is one direction. So let's be more conservative and try to guess a smaller number. Unfortunately, if we guess a number which is 4 times smaller than the real distortion, then our algorithm specifically completely fails and provide an unbounded competitive ratio and may get unbounded competitive ratio. So we don't know how to take a robust algorithm and create a distortion oblivious algorithm. Now I'm going to discuss just to discuss the error measure. So our measure is the maximum distortion. So we look at the job whose distortion is the largest compared to its real size, and our algorithm depends on this number. And the question is why not to have an algorithm whose error depends on the L1 distance, the sum of the distortion, instead of the maximum distortion. So the reason is that we want to make our error as small as possible, and then our algorithm will be would be much better. So if we define the error to be small, then the performance of the algorithm is better. So we prefer, and since the maximum distortion is always smaller than the L1 distance, the sum of the distortions, it's better to have an algorithm whose competitive ratio depends on the maximum distortion versus an algorithm whose competitive ratio depends on the L1, the sum of the distortions. So now you should obviously ask me why not to use average distortion. Average distortion, which means we look at each job, we look at what its distortion is, its size compared to the estimates versus its real size, the ratio, and we look at the average distortion. This would be certainly better than the maximum distortion. So here we get a smaller number, and if we are able to get an algorithm whose competitive ratio would depend on the average distortion instead of the maximum distortion, then our algorithm would be even better. Unfortunately, we can design an example where only constant number of jobs have a high distortion, and then we have infinite or very large number of jobs whose distortion is 1. Actually, they don't have any distortion. So if we look at the average in the limit approaches 1, the distortion, the average distortion, because we have only constant number of jobs with high distortion and all the rest are 1. But we can provide a lower bound that in this case the distortion will still be equal, unfortunately, to the maximum distortion. So there is no way to get an algorithm whose competitive ratio would depend on the average distortion versus the maximum distortion. So even if we have very few jobs which have the wrong estimates, we can get into a trouble. And even if all the remaining jobs forever will be correct, we might have, of course, in the worst case, I'm not saying that always, in the worst case, and of course, in very contrived input, we can have a competitive ratio which is large, although almost all jobs are correct. Okay, so this was the introduction. And now in the remaining time, I'm going to describe the algorithm. So again, I need to describe for you 2 algorithms, one for the unweighted case and with unknown distortion, and the other is for the weighted case with known distortion. So first of all, I'm going to describe the intersection of the 2. The easiest algorithm, which is unweighted case, but with known distortion. So this is easier than the 2 results that I mentioned. Unweighted case is all the job have the same importance. I just want to minimize the sum of the flow time, of the sum of the response time. And we know maximum amount, that is the maximum bound of the maximum distortion. So here is the algorithm. To define the algorithm, we use just visualization of the jobs. Each job will be visualized as a rectangle. Its height going to be 1. In general, it's going to be its weight, but since we are now in the unweighted case, all jobs have the same importance, the height of the rectangle will always be 1. And the width is going to be its processing time. And the processing time is always shrinking, because once we process the job, the remaining processing time becoming smaller and smaller. So the rectangle will be shrinked in its width. So each job is described as a rectangle. And obviously the width is the processing time as well as the area. Now, the unweighted algorithm with known distortion is as follows. We have 2 types of bins. One of them is called F, it's the full jobs, and the other is a bin for a partial jobs. So here there are jobs which haven't been processed yet at all, and here the jobs already started to be processed. So the width might have been slightly shrinked. And now incoming jobs, when we get a new job which is released over time, we always put it in the full bin, and later I will describe how to put it in the full bin. And processing is done only through the partial bin. Only jobs in the partial bins are going to be processed. And obviously, at some point of time, we need to move jobs from the full bin to the partial bin. And the way to do it is when the number of jobs, in general, the weight of the jobs, now the weight is equal to 1. If the number of jobs here is larger than the number of jobs here, so we move 1 job from here to 1 job from here, and I'll describe it immediately how to do it. So let's do 1 step at a time. So first of all, let's look what happens when job is released. Again, we have when job is released, it's going to enter only the full bin. So we have a job queue. These are the estimates. Note that we know only the estimates. We don't know the real processing time of the job. The real processing time might be different than the estimates. For example, 2 jobs, one job might have a higher estimate from another. Job A might have a higher estimate compared to job B, but job B might have a longer processing time compared to job A, because we have estimates and we don't have the real processing time. So when we get a new job queue, we want to put it at the top. Okay, the thing is that we want to have a preference to shorter jobs, and want to put the shorter jobs over on the top, but we are not sure about the real processing time. So we are going to identify jobs whose processing time is certainly shorter than the new job which has been added. So let's say that we have here 3 such jobs, Q1, Q2, and Q3. How do we know that the processing time is shorter, certainly shorter than Q? Because the estimates has a factor of at least mu. If the ratio between the estimates is at least mu, we are sure that Q1, Q2, and Q3, all these jobs are going to be shorter than Q, and we want to put the shorter jobs towards the top of this bin. So the way to do it is actually and this is very depending on the proof, is to do a cyclic shift. So Q1, I'm going to put Q at the bottom instead of Q3. Q3 is going to move to Q2. Q2 is going to move to Q1, and Q1 is going to be at the top. Specifically, this is the example. I'm going to show it again because it's a bit confusing. Q is going down, instead of Q3 is going here, Q2 is going here, and Q1 is going here. So I'm going to do what's called cyclic shift among only the jobs which are certainly shorter than Q. Note this job is not necessarily shorter. It actually might be shorter, but we don't know if it's a shorter or not shorter. And this does not participate in the cyclic shift process. So this is how we deal with jobs which are released. And then at the top of the bin, we have jobs which are supposedly shorter. I mean, the jobs are sorted, but not precisely sorted. It's approximately sorted, because if job is really as a large estimate, it will be in the bottom, and a small estimate, it will be in the top, but it's not going to be a complete sorting, because we have this error of mu. So this is how we maintain the bin with the full jobs. And what about processing? Now, which job are going to be processed? The job which is processed is going to be the one at the top of the partial jobs. Again, at every point of time, only one job is processed, and this will be the job at the top of this bin. And specifically, in some sense, it's a LIFO, because jobs are going to move from the full jobs to the from the full bin to the partial bin. And actually, in some sense, it's a LIFO. The job in the partial bin are processed in a LIFO fashion. And there are also other possible choices, but which works, but the LIFO is the simplest. Now I only need to describe how to transfer a job from the full bin to the partial bin. So every time that the full bin has more jobs than the partial bin, then I'm going to move the top job, which is supposedly the shorter one, not necessarily the real shorter one, but approximately the shorter jobs. I'm going to move it from the full bin, from the top of the full bin to the top of the partial bin. So in some sense, these two bins have exactly the same number of jobs, or alternatively, the partial bin has one more job, because once the full bin has already one more jobs from the partial job, then we move a job from the full to the partial, and if job ends, so this one becoming shorter, again, we are going to move a job from here to here. So this is the whole algorithm. And I'm not going to describe the proof, but this is only the description of the algorithm. A natural question would be, why I'm really going back, why I'm really maintaining here approximate sorting, and I'm not sorting it according to the estimates. This would seem more natural. Why I'm insisting of keeping jobs with larger estimates above jobs with smaller estimates. And the reason is that, unfortunately, if we sort the job completely, and the error is, for example, distortion is 4, this algorithm completely fails. So surprisingly, we need to maintain approximate sorting and not real sorting. So this is not lack of impossibility to prove. This is really required in the algorithm. So now I'm going to describe how to change the algorithm to the weighted case. So again, as I mentioned, this was the algorithm for the unweighted case when we know the distortion. Now I'm going to switch to the case of the weighted case with a known distortion. So here I'm actually going to round the weights of each job to a power of 2. So please note that the weight of the job, the exact weight of the job is not really so important, because if we round the weight of the job to the next power of 2, we only lose a factor of 2. This is very different than rounding the processing time. Rounding the processing time is impossible. If we have a job of size 1, and if we round it even to 1 plus epsilon, or let's say we have jobs of size 1 minus epsilon, and we round it to jobs of size 1, the flow time, the response time, can increase from linear to quadratic. So we are not allowed to touch the processing time of the job, and the algorithm is very sensitive to the exact processing time, while it's not really sensitive to the weight. So this is why we are allowed to round the weight, but not really round the processing time. So here what we do is actually we have a pair of full bin and a partial bin for each weight class. So we have here weight class of 1. So again, the height is the weight. So here the jobs have weight 1, here the jobs have weight 2, and here the jobs have weight 4. And for each class, for each weight class, we have a pair of full jobs and partial jobs, and we behave as precisely in the unweighted case for each such pair. So the only difference is which job we need to process, because before we had to process the job from the partial bin, but now we have multiple partial bin. So we just process the one with the tallest bin. So in this case, we're talking about this A4. So this is the algorithm, and again, I'm not going to talk about the analysis because it's a technical and delicate. I'm not much time is left. I'm not sure how long. I'm only going to very briefly talk about the distortion oblivious algorithm. So again, let me remind you here, I had to assume that I know the distortion or upper bound of the distortion in advance. The more complicated case is that we don't know the distortion in advance, and here we only know how to handle the unweighted case. So I'm not sure, do I have here only 2 minutes or I have more time? Because if I have 2 minutes, there is no way to describe the algorithm. So the algorithm is a bit, I've just given pictures. We have estimate, we classify the jobs according to their estimates. And we have a nice type of job. This is a snapshot of the system.
Yossi, you have 7 minutes, so 5 minutes.
7 minutes, okay, sorry. So let me, if I have 7 minutes, I'm actually, let me say something about the idea of the proof, and not necessarily about the description of the algorithm. Is as follows. If we, let's say that at any point of time, an algorithm has delta t pending jobs, while the optimum has delta star t number of pending jobs. So if we are what's called local competitive, which means that we have C more times, at most factor of C times number of jobs compared to the opt, then this would imply a C competitive algorithm. And the reason is that the flow time is actually the integral over time of the number of live jobs. The thing is that we actually also need the other direction. In order to prove a C competitive algorithm, we need to be also local competitive. And this is with some disclaimer, which I'm not going to describe. So let me just describe the algorithm very briefly. I'm looking at the jobs. I'm dividing them according to their processing time, according to their classes. Each job, according to the class, is processing time between 2 to the I, 2 to the I plus 1. So here are the shorter jobs, and here are the longer jobs. And I have full jobs, which are empty circles, and partial jobs, which are full and polygons. And there is difference between the types, but I'm not going to have time to describe the difference. And we are going to have at most one partial job per class, because partial jobs are not competing with each other in the same class, but we might have many full jobs in a class. And the natural thing is that we want to have a preference to shorter jobs, jobs with shorter estimated time. And at any point of time, you are going to process the job with the lowest class, which is partial. So this is like a snapshot of the jobs. And here we have some full jobs which are empty, some partial jobs which are full, and we are not necessarily going, like naturally we want to prefer the shorter job to process the shorter jobs, but are not necessarily going to do it. Sometimes we are going to process jobs which are close in the next class and not necessarily the one that we expect it to be shorter. So one natural algorithm is to run the lowest class first, which means have a preference to the jobs with a shorter estimation. This is a very natural algorithm. Every time I have preference to the shorter one, but the problem with that is that I might be left with tiny part of jobs over time, and I'm not going to finish every job. So we need something, there is something else which is called a special rule, and I don't have time to describe it. And actually our algorithm, it's called a zigzag. Sometimes it uses the lowest class first, sometimes it uses the special rule, and sometimes it changes the job from one option to the other. And obviously I don't have time to describe it, so I'm going to skip it. Yeah, and of course also the proof and conclusions and open problems. So conclusions, again, I was talking about minimizing the total flow time, total response time. For the unweighted case, we have mu log mu competitive algorithm and almost matching lower bound. For the weighted case, we don't have a distortion oblivious. We need to know an upper bound on the error in advance, and we get appropriate bounds. So I'm switching to open problems, and we'll be finishing with the open problems. So, okay, this is, as I said, the most interesting open problem is to obtain a distortion oblivious algorithm for the weighted case. This we don't have any idea how to do. Another more minor problem is closing the gap between the upper bound and the lower bound for the distortion oblivious case. Okay, there is also difference between there is a gap in the robust case, but this is more interesting, but it's a minor difference. And the third problem is to deal with multiple machines. Here we have recently a new paper which will appear in Isaac and deal with multiple machines. In some sense, multiple machines, like it seems that multiple machines is going to be harder than a single machine, but surprisingly simpler because the competitive ratio to begin with multiple machine is worse than a single machine. So we are shooting for a worse result because the competitive ratio to begin with is worse. So we actually multiple machines, since we need to shoot for a worse result, it's easier compared to a single machine, which seems a little paradox, but this is the case. That's it. Thank you, and I'm happy to answer questions.
We have time for one quick question while Ben is preparing.
Yes, thank you. Hi, this is Z from CMU. Great, I really enjoyed this talk. I had a question about the distortion definition kind of being one, even when you have a sort of all the jobs estimates are scaled. And the question is basically, do you have any insight in sort of what your algorithm ends up reducing to in that case, and whether, and like, does it simplify or anything like that?
So again, I mean, the fact that if all jobs are scaled, it's a feature, it's not a bug, because you are, in that case, even if your estimates are wrong, but they are all of them have the same scale, you get a constant competitive algorithm. So even if your estimates are 1,000 times the real size of the job, you still get one or two competitive algorithm because it's uniform over all jobs. So it's a feature, it's not a bug in that sense. It's a feature of the algorithm. You get a better bound. And the reason for that is that it's, yeah, I mean, I wouldn't say that the algorithm is behaves when you scale the numbers, the algorithm does not behave exactly the same, but it's but the order remains in some sense the same. I'm not sure if I replied to what you precisely asked.
Steve gives a thumbs up. Hi, it was a great talk. I had one question about the distortion. So this came from the motivation of you don't know what your job processing times look like ahead of time. So, you know, distortion gives you some like leeway in your assumptions. But how might you like know distortion ahead of time, like in order to either like A, use the right algorithm in the robust case, or B, know how tight your algorithm is, like know like the bounds on it. And what happens if like maybe your jobs are coming from some distribution, or there are times they're coming from some distribution where, you know, like maybe it's not exactly bounded, but like it's like close to its expected value or something.
Mm-hmm. So again, for the distortion oblivious algorithm, you don't need to know the distortion in advance. The performance of the algorithm depends on the actual distortion, but you don't need to know the distortion in advance. You just run the algorithm, and the performance depends on how bad was your estimates. And during the algorithm, you really discover how precise are your estimates, because you run the jobs. So, and you're right about the robust case. Robust case, you need to know mu in advance, which is tricky, and it's not clear how to do it. As I mentioned in the beginning, typically you assume that you have either a prediction on that, and you look at historical information about these jobs, and you can, maybe with high probability, you can get a good estimate. And from time to time, your algorithm will fail if the estimate is incorrect, assuming you will use the robust algorithm and not a distortion oblivious algorithm.
Thanks, Yossi. So in the interest of time, let's take other questions over email, and let's thank our speaker again.
Okay,
So
thank you.